Good evening, dear viewers. Welcome to the first BH Futures webinar for the month of June. Tonight's speaker is a respectable Professor Seid Korić, with a PhD in mechanical engineering from the University of Illinois, where he currently serves as a research professor in the Mechanical Science and Engineering department. As a young engineer, joining the team of humanitarian workers from the Research and Development Center for Gas Technology, IGT, in Sarajevo, he served as an engineering intern in the facility, helping to set up and install natural gas distribution in the then war-torn Sarajevo. Professor Korić has 23 years of experience at the National Center for Supercomputing Applications, NCSA, conducting cutting-edge applied research and providing consulting for the national, industrial, and academic computational communities on the center's HPC platforms. He is currently the technical assistant director of the NCSA, where he additionally leads the research projects on the NCSA petascale high-performance computing system of Blue Waters. Tonight, he will introduce us to supercomputing, that is, how it works and where it has been used. He will discuss data-driven discovery, which has been made possible in recent years by our ability to generate, collect, and analyze big data. And as always, we encourage you all to write the questions in the QA section or the chat, and they will be addressed after the presentation. Seid, thank you so much once again for being here tonight.
Thank you, Anna, too. And prvo da se obratim na našim lijepim mjestima. Prvo, znači, pozdrav svima, da se zahvalimo prvo organizatorima, kolegi Čustoviću i Eni Džemili i Ivani Jeftović iz BH Future fondacije, kao i svima koji ste se pridružili, našto kolegama i kolegicama u našoj lijepoj Bosni i Hercegovini, znači dobro večer Bosna i Hercegovina, gdje god da se nalaziš, nam da nas gledaju također ovdje u Americi, u Europi, u Australiji. Now we're going to switch again back to English, right? So yes, the talk is about, I thought a little bit introduction to supercomputing. Not everybody knows what supercomputing and HPC is, but then we're going to switch to actually some of the examples. We are lucky here at the National Center for Supercomputing Applications at University of Illinois that we have one of the largest supercomputers in the world. So I'm going to show you, and I was leading some of those projects. So I'm going to show you some of those extreme scaling examples on Blue Waters and what we have solved there. Then I'm going to talk about the rise of the 4 paradigms in science engineering, which is data-driven. And then I'm going to show you from my research some of the examples of the confluence of classical modeling simulation with artificial intelligence. And then my understanding is, in the meantime, we're going to get some questions from you. Anna is going to collect them, and then we're going to try to answer them live, right? Okay, so going now to talk about, this place where is my home for 23 years, 24 years since I left Sarajevo, is the University of Illinois at Urbana-Champaign. It's one of the largest universities, public universities in the United States, particularly here in the Midwest area. So you can see a little map here where the state of Illinois is. Everybody knows about Chicago, right? But we are kind of in a triangle of 3 big cities besides Chicago, which is 140 miles north from us. Indianapolis is 120 miles east from us, and then St. Louis, where actually many Bosnians live, is about 170 miles south from us. And what is University of Illinois known for? Well, for example, it gave us a transistor. Everybody now runs on transistors, right? It's also home of superconductivity. It was found that conductivity can be really, scaled to 0 resistance, and it has lots of usage nowadays in modern science and engineering. It's also home of LED. Professor Holeniak, who is still alive, he's actually inventor of LED lamp. I think about all those monitors that we have on laptops and displays nowadays. They are all LED invented here at University of Illinois. We are also in the middle of big corns, big flat, fields, and There's lots of agricultural research happening here at University of Illinois. So among many things, they actually invented the sweet corn, corn which is sweet, and it's very tasty too. And then when it comes to these technological gizmos, Mosaic, what I'm going to talk shortly in a second, is actually invented at NCSA where I live, which is the first successful browser that kind of launched the whole, internet and web browsing in the world. Plato, PayPal, Yelp, YouTube, MS Flight Simulator. I'm sure you're going to recognize some of these names. They either started as students who actually started coding them, or later on, they actually started spinning up companies with those things. Okay, so let's talk about NCSA, which is one of the departments here at University of Illinois, where I work. So it stands for National Center for Supercomputing Applications. Originally, it was funded by National Science Foundation, which is an agency here, a government agency here in the United States that funds science engineering. And we opened our doors in 1986. So that means the whole NCSA now is actually 35 years old. Traditionally, it hosted some of the most advanced open science cyber infrastructure in the United States. And also, very important thing in our name is applications. So we, rather than machines, we are very proud of our people expertise that we provide in consulting for the national academic and industrial research communities. I already mentioned Mosaic. So if you come to NCSA, you can see this plaque here, which says that the first successful web browser was actually invented in NCSA in 1993. And then, spin-off was organized, which was actually Netscape, and then Microsoft, Explorer was actually, based on Netscape and so on. So without NCSA, everybody thinks, it won't be, it will be delayed. The whole process of actually adopting internet and web browsing would be heavily adopted, and we were really proud of this legacy that the first web browser were actually invented at NCSA. Also, when it comes to supercomputers, especially on the Linux area, we deployed in 2001 first Itanium-based Linux cluster, which was again funded by NSF, which allowed researchers in the United States, border to border, actually, to be able to tap into the power of Linux clusters and HPC. And then a couple of programs, originally that was called TeraGrid, and then now Seid, which actually enable faculty and students from all across the United States to get access to HPC centers, not only NCSA, but also there is a whole alliance of these centers where they can actually get the, to compute on these HPC systems, and also to get expertise from HPC experts. So both of them were actually, PI was here, principal investigator was here, and NCSA still it is here. You can see that the Seid started in 2011 and is still going on. We are particularly proud that we deployed and supported the first world sustained petascale system of blue waters. I'm going to say later on what petascale means 10 to the 15 floating point of operations per second, which is a really, really powerful machine. And, the place where I particularly work is actually industry program called NCSA Industry. So we are the home of the largest industrial supercomputing program in the world, working with many companies from many sectors. Okay, so let's talk a little bit, how we actually define what supercomputers or high performance computers are. So you can see a little chart here. It's a moving target, needless to say. My iPhone, which is not the latest one, number 8, right? It's You know, it would be supercomputers 20 years ago when I started as a grad student. So basically, we defined it, supercomputers are largest and fastest computers right now. And supercomputers at least 2 orders of magnitude or 100 times more computationally capable than, you know, mainframe, PC, workstation, and or laptop or whatever you want. Supercomputers also are known as a high performance computers. So those two terms, supercomputers and HPC, are interchangeable, as you can see many times. Actually, I'm going to use either one of them. So who is using high performance or supercomputing? The answer is anybody whose problem cannot obviously fit on a laptop or a PC or desktop, and it will take very long time to run on a PC. So think about all of these things that are incredibly small, like a molecular science and materials, quantum mechanics, all the way to universe, where all those you know, equations, relativity, and etc. in astronomy, they're actually from 1 to infinity. So you know, the more computing power you have, the better you're going to be with these areas. But you know, everybody else in between, including us in engineering, are also using heavily supercomputers. Some other areas well known, weather and climate change, geoscience. Of course, you know, nowadays we are hopefully emerging from this shadow of COVID. But you know, HPC has been heavily used for COVID to predict, you know, spreading, but also, you know, before for other things which are pertaining to health and life science. The dark side of HPC, which we like to say, you know, although there is nothing dark there, is actually finance modeling. It's a well-known that you know, Wall Street and all of these big financial corporations, they are heavily using HPC all of these years, and now even more. Okay, so let's talk about you know, how actually supercomputing or HPC, how it works, you know, why so high performance. So one analogy that I like to use when I actually teach, you know, new generations on about HPC is, if you are a fan of Formula One or any of these racing cars, you know, when the car actually goes into pit stop, you know, the bunch of these guys working in parallel all the time. If just one person is taking care of, you know, Lewis Hamilton or whatever, it will take very long for him actually to, you know, leave the pit spot. You know, so the idea is actually doing many things in our case on HPC computing at the same time. And another analogy is, you know, if this person is fishing, you know, he can fish maybe 1 or 2 fishes, you know, but if a bunch of these guys are fishing on different areas, they will be able maybe to fish more. Of course, you know, a smart student will ask, oh, what if there is only 1 fish? Which is a really good question. You know, then we are talking about actually limited amount of you know, computing needed, for example, in HPC, which is going to just create slower time and overhead. So not everything is you know, eligible for HPC, for supercomputing. You have to have lots of this independent tasks that you can actually parallelize. One thing on the right hand side you can see is in engineering, for example, when we are doing some kind of stress analysis or fluid analysis, we actually do the domain decomposition, where we decompose, you know, this big mesh in a chunks, and then each chunks is actually run by different processors, and then that's how we actually get savings, tremendous savings in time and in resources. So how a supercomputer look like? So basically, it consists of many nodes, computers or nodes, what we like to say, and they are, you know, put in a special, you know, racks. They are mounted in special racks, and of course, it has to be some kind of, you know, network so that they actually exchange the data all the time, and they're usually very fast nowadays. They also have to have a file system. In the past, they had the independent file system, which was a pain. Now they have shared file system, which is shared by all the nodes. So no matter which nodes you are on, you're going to see the your files just like any other nodes, which was connected with your job. And then when it comes to software, that allows the nodes to communicate to each other, and that we are able actually to program these things. So some of the popular ones are message passing interface, which is called MPI, OpenMP, OpenACC, which works on GPUs, and many others. Actually, nowadays there is also parallel Python and parallel Python libraries, which are very easy to use. System software reserves the resources for individual users. So if I am the only user on, let's say, Blue Waters, it'll be easy, right? But there are always thousands, if not tens of thousands users. So system has to be able actually to allocate and to put these jobs in a queue and then run them as your time comes actually for running that job. So let's, very briefly actually, talk about this evolution of HPC architecture. I think most of you guys are, even either in your 20s or 30s, you may not remember this, but I do. When I came to United States, for, at least 10 years or maybe less, a little bit, these computers, even PCs, they would coming every time, more and more powerful, talking about 100 megahertz, 500 megahertz, 1 gigahertz, 2 gigahertz. Nobody cared really too much about this parallel computing because, they will coming 2 or 3 times faster. And there is a whole law, which is called Moore law, which says that every 2 years, chip density is continually increasing. Unfortunately, at around 2003, clock speed couldn't keep up anymore. There were also some physical limits of the material. So instead of increasing the frequency and power, people started actually putting more CPU processors. So that's the time where we actually started talking about dual cores, multi-core, multi-sockets, and one extreme is actually GPUs, where you have thousands of these chip nowadays, stacked together. And it's fair to say, even my laptop, which is, I don't know, quad core nowadays, is a parallel computers. So the question then becomes, how do you actually program software take advantage of these computing architectures, parallel architectures? So this is a little bit of a landscape again. Message passing, MPI, OpenMP, which are special libraries that you can actually link with normal C++ or C code or Fortran code if you are of older, age. They actually work very well with this parallel computing. But then on GPUs, for example, CUDA, OpenCL, OpenACC are dominating now. There are some other more like exotic things like Unified Parallel C, CoreI, Fortran. And as I said, with all of this deep learning AI, vendors are starting actually, offering also parallel Python and parallel based libraries like NumPy and SumPy and all of these things. So let's, I understand lots of our audience today is actually from computer science programmers. So I wanted to share very briefly how those actually parallel programs look like. So first, let's start with OpenMP. Again, it's an application programming interface supported by C, C++, and Fortran to provide on shared memory. That means on one node that has many cores, but we are not going into different node. We can actually, enable parallel, execution here. And you can see here, this is what we like to say fork. So it's actually, parallel part of the code. We are actually spawning these threads. And then, each thread is doing some different independent task. It's very important to find a part of the program which is actually, it doesn't have some kind of data dependency, time dependency, which can run in parallel. And I'm going to show you soon example for that. Again, you are putting these pragma OMP directives closest, what we like to say, into normal C program, and then, compile with OpenMP, and that's how we get those parallel programs. And then we, on the runtime, we are deciding how many threads we want to run all of this with. So I'm giving you an example of calculating pi. So one way to calculate pi is actually do some kind of numerical integration for this function of 4 over 1 over x squared. So if you do old-fashioned way, you're going to have arctangent 1 minus arctangent 0 on the domain of from 1 to 0. You're going to exactly get the pi. So if we can actually integrate this function from 0 to 1, you're going to get exactly pi. So you can see here I'm using mid point rule, and you can see that I'm putting here these pragmas. I'm telling program, this is going to be my parallel part, and then in 8 loops I'm actually executing 2 threads course in parallel, and each one of them. So this is a thread 0, and this is the thread 1. So thread 0 is executing loops 1, 2, 3, 0, 1, 2, 3, and then thread 1 4, 5, 6, 7. And this is simple, you're not going to get much speed up here, but think about if we have a really big problem with many of these, of these rectangles that we have to calculate the surface underneath, and then we can actually use more of these threads. So this was OpenMP, and then for MPI, which is actually much more powerful, but also harder to program, is this, again, standalone library for exchanging messages between the processors. So why is important is exchanging messages? Again, remember when I was talking about HPC systems, so they have nodes or independent computers, and they are all on a network, so they have to communicate each other. So very, popular way to do that is actually through this message passing interface, where, these nodes and even processor on these nodes, they are actually exchanging data between each other. MPI supported with C and C++ and Fortran, and has over 140 functions, but you don't have to know all of them. I think if you know, let's say 20 of them, you're going to be pretty good actually to write the parallel program. So same problem that we are solving again with MPI. So you can see, the program right away looks, there's more syntax here. So some of these things here, we are actually initiating MPI, and then the master process, which we called rank 0, it's actually asking the users how many of these intervals you want to calculate. And then, this MPI broadcast is actually, broadcasting or sending message to other processes about, a number of these intervals. And then each process adds up the height at the middle of every non-processor interval, finding these x1, x2, x3, and multiply by the step size. That's how we get the actually surface all of these integrals, which are approximating the surface of all of this curve, and then PI. Finally, in this MPI reduce, the master, the 0 rank is actually getting, these numbers from each processor. Again, this is a simple problem where, there are only 2 processors and there are 10 intervals. So the process 0 is going with the first interval, third, and so on, and second. If we have more, it will be like if we have 4 processors, this guy would be 0, and then 4th, and so on. But the idea here is actually they are all working in parallel, and it's pretty. In this case, it's pretty balanced. They're going to have the same amount of work. So you can think they can really scale this problem and solve it much faster than if we run just on one core, one processor. So speaking about that. First thing that we look at HPC or supercomputers is actually a scalable speed up, which is showing us walk log from one core divided by wall clock of, you know, many course, whatever course you are using. So speedup reveals the benefit of solving problem in parallel. Every problem has some kind of sweet spot here. And one would naively think, you know, that if I'm run on 128 course here, so my execution is going to be 128 times faster. Unfortunately, you know, there is life is not like that, you know. So real speed up is always smaller than the theoretical. There are serial portions of code, of course, that we cannot parallelize. I was mentioning load balance, so every of these working processes has to have the same amount of work to work with. Otherwise, we're going to have unbalanced thing. You know, network itself, you know, it's fairly fast nowadays, but still has latency and bandwidth. And then, you know, there are some specific in parallel implementation, code is doing I/O, all these things. So it's always deviates, but, you know, you can see, for example, here on 32, it's pretty good. From 32 to 64, there is very little gain, you know, going, but, you know, probably the computational cost is much higher, you know. But if you have your own supercomputer, you don't care. You actually go to this one. If you are in a company which is paying for the time on supercomputers, probably going to be here or here. Okay, so so let's talk about supercomputing in science engineering. So this is actually, I was still grad student, young guy, when I went to this conference, and Professor Tom Hughes, he's retired now, or he's still active, I'm not so sure. But he said an interesting thing. He said, you know, this was 2003. I mentioned, you know, this was the time where they started, you know, introducing dual cores. So he said that, you know, supercomputers will be always too small and too slow, even when they become size of the football fields. So I was really puzzled what he was talking about. But then when I went to work actually at NCSA, especially with industry, I could see that, you know, all up-to-date, most powerful supercomputers, you know, they are good, but they, we are just scratching surface some of these things. So I'm giving you an example from another conference called International Supercomputing 2014. One of our partners, Dr. Yun Ho from Rolls-Royce, he said, I have a dream. In my dream, I see the whole, you know, virtual engine simulation being done in design, and you know, quick calculations on the back of the envelope show that actually for this kind of calculation, we will need 1 trillion degrees of freedom, means to solve 1 trillion equations very frequently. 1 billion cores probably will need for that. Right now, the best supercomputers are order of million, of course, so we are 1,000 times away from this dream. So let's talk about you know, work that we have done on Blue Waters. I already mentioned Blue Waters, which was the first sustained petascale system in the world. Petascale means 10 to the 15 or quadrillion floating point operations per second. Just to give you an idea, floating point operations, for you who are computer scientists, you probably know. So it's if I'm you know, doing some elementary calculations between two floating points numbers, decimal numbers, basically 1.1 times 2.2 is 3.3. Usually it will take me probably 1 second, right? But there's no way I can do that for a very long time. So what Blue Waters can do in 1 second would take actually 31 million years, you know, for a human to actually calculate that. So just to give you an idea, you know, how powerful are these supercomputers. And right now, if you look at what they call top 500 list, I think US is still, US is again #1, and for a while it was China. And they are already talking about hundreds of these petaflops, and we are approaching exaflop, which is 1,000 times petaflop, you know. So, and there is always race for that. But anyhow, back to this Blue Waters time that we did from 2013 to 20. Lots of these things, you know, when we started, you know, people didn't believe that engineering code, especially in finite element CFD, they can you know, scale so wide. So in a sense, we were technological evangelists And we showed that there is a feasibility of efficiently solving extreme size, real-world multi-physics, geophysics problem on a petascale level and potentially exascale. And all of this work actually added tremendous value to future science engineering, high fidelity simulations, design, and research. So you can see, for example, we got one of the top supercomputing achievement awards back in 2017 for that work. We also work, our genomics team, they work with H3 Africa Research Consortium, make it possible to discover genomics variations on over 300 deeply sequenced human samples from Africa to help construct genotyping chip sequence for African population, which is kind of, you know, most of the time, you know, focus is always on Western Europe and the US, but in this case, you know, the work, really good work was done with this H3 Africa on blue waters, actually, for African nation. Okay, so I'm just going to give you an example, some of these calculations. So the ALIA code is actually from Barcelona Supercomputing Center, and you know, I work with them. We scale the code on 100,000 cores on blue waters. We solved the problem of 3.4 billion elements inside. So you can see, hopefully it's going to start. Human heart. So human heart with all the details. So we solved electromagnetic, you know, propagation coupled with mechanical response. You can see, you know, it was beating pretty well. And apparently later on, you know, this model was used actually for some medical purpose in Europe as well. The second one is more of industrial importance, which is a kiln furnace. You know, when you are making cement, actually you're using this furnaces, and it's pretty long, actually, I think between 50 and 100 meters. So we actually created a mesh to capture the turbulence, and it's very hard to capture the turbulence, but we did. And that one has 4.22 billion elements, also scale 100,000 cores, but with 90% efficiency. And that's just to give you ideas for these calculations. It will take close to 18 years on a laptop like this one that we actually did those calculations in less than 2 hours on blue waters. Give you another example. This is actually, again, a Rolls-Royce engine model from our partner from UK. They have also business here in the United States. So they were interested in this LS-DYNA you know, code, and they did some just thermomechanical analysis of the jet engine. So we worked with them for a few years. I was actually PI on that project. So you can see how we iteratively improve the code so it can scale on very large machines. And you can see this is a log scale. So you can see that initially at between 4 volts and in their computers, best computer back in 2015, Rolls-Royce, it took them 1,000 hours to do these calculations. We actually went to 10 hours. And this was combination of power of HPC, but also, you know, the improving the code. Probably the largest and the best, you know, case we had that Wall Street was talking about was actually from ExxonMobil, which is a big energy company from United States. So they come up with the code. They suspect it can scale very well on big machines, which is calls for reservoir simulation, or what we call in CFD Darcy equations, which is a flow through the porous media. So it took them 3.5 months actually to run on their machine. So we actually use entire blue waters, which was 700,000 processors we used with this code. How did we do it? Well, again, machine is paid by the government of US. You know, they don't allow for somebody to dominate like this. But that was one of those examples when the machine was in maintenance. So we said, okay, once the machine gets from maintenance, don't let users on it. Let's try for 10 minutes, you know, pray to God that no node is going to go down, because they do, right? It's a huge machine. So we were actually lucky, and running for 10 minutes, we were able to see the scaling. And ExxonMobil itself says, you know, the ROI, what I like to say, which is the return of investment, was over $1 billion for this run. We wish we could see a fraction of that money, but we didn't. We were just we are not for profit, right? We were just they were just paying their membership fee and for this run, but they didn't, of course, pay for ROI. But down the road, they know. I think they are acquiring their own machines, big machines nowadays, actually. So this was a great exercise for them. I think Professor Torlak is also joining us and listening to this. So this is actually very dear to my heart. Collaborations that we did with University of Sarajevo, with mechanical engineering department there, with Professor Maurice Torlak and Almin Halac. So they created actually mesh of this, flow, turbulent flow, pretty high Reynolds number, 50,000. Around this sphere, and we compare LES model, which is a very computationally intensive model, and DES, detached eddy simulations, and we proved how actually DES is pretty good. Actually, it can give us almost good results as LES, but under much less cost. So HPC on our side of the pond here in the United States at NCSA, which was used, Blue Waters and iForge systems. And we presented actually back in 2017 and in 15, we presented this work. One was the big turbulence conference in Sarajevo, and the other one was ASME here in the United States, so very proud about this. And we have plans to actually work more on these projects. Okay, so how are we doing with the time? This is just a simple example of a large statistical HPC analysis. It's not all about modeling simulation. So this is actually power statistical analysis, and it was done in R, which is a very popular statistical tool nowadays. And so the partner came up with this problem, trying to, optimize where they're going to put these, pesticides and all of this, lots of statistical analysis. And we grabbed their code in R, which was more like a spaghetti code, 50,000 lines. And we have somebody on our team who is actually a world expert in R. So she was able actually to, put this code in 100 lines. And also run on, iForge, which is industrial HPC system. And partner at the end was really happy. It actually went from 175 days that they never were able actually to run to less than 3.5 hours. So they were able to get the results. Everybody is talking about GPUs, right? So this is actually another area where our genomics team was used GPUs. It's new variant calling tools. Variants of genomics are unfortunately popular nowadays because of COVID. So there was a research group that actually ported them to GPUs. But then we were kind of independent investigator here actually that grabbed that code and ran it on our GPUs, and we really showed that you can see the blue lines. Very little time was used compared to GATK, which is kind of standard on CPUs. Almost like 100 times faster as actually was. And right now we are working with industrial partner test against their variant calling tools. Okay, so it comes to my point now to talk about this fourth paradigms in science engineering. So long time ago, we didn't have equations. We were just looking at empirical science, then equations come, but for quickly realize, they are hard to be solved in a closed solution. So we started using computers and big computers. And then around, dawn of this 21st century, actually, we started using this data-driven approach where we are coupling this classical numerical analysis with data analysis and data analytics and machine learning and all of those things. So one of the big names from this side of the pond is Professor Andrew Ng from Stanford University, who is actually a founder of Coursera. And he said AI is the new electricity. And another one is, it's developing very rapidly. So what is cutting edge nowadays in an AI will become commodity computing in just a few years. It's really happening in that pace. So one would ask, we have machine learning for so many years. So what's the difference? Now you have all these deep neural network, right? So the big difference is actually if you have lots of data, and if you employ some of these traditional machine learning algorithms, your accuracy is going to become flat at some point. But if you actually start using neural networks and you actually started becoming, creating more and more deeper neural network, your accuracy is going to go really up. And like everything in life, there is no free lunch, right? So what is happening here is you need lots of more computing, and that's where HPC comes in place for this neural network. So you can see, this is actually our benchmark. So you can see random forest, which is a very popular machine learning algorithm. In terms of accuracy, the machine learning was, deep learning was much better. But the price that we pay was actually, you can see that runtime in seconds was much higher on with neural network. But of course, if you have GPUs, if you have big machines, this can go down too, right? So let's talk quickly about deep learning. It's actually got the idea from biological tissue, from brain, all of those neurons that are connected. So we are basically creating some functional, we are connecting input and output and some relationship. So this is what we like to say feed forward, where information is going through these layers, and and they have weights and biases, basically linear algebra. But at the end of this, each of these layer, there's also a nonlinear function, which we like to call these nonlinear functions. Actually they are enabling the nonlinearity to take place between input and output. And then in the back propagation, actually we are getting the gradients, and we are optimizing all of these weights every time. And at some point, we say we have enough precision. We train enough with training, then we grab the data. If we don't cheat, we grab the testing data, is actually test all of that and see how it works. So choosing and applying best machine and deep learning algorithm is very popular nowadays. So I'm giving you quickly example of one of our industrial partners. They are actually doing machine. They are actually doing the mixture to get this octal number of 87. And you can see they have non-machine learning prediction. These blue ones. They provided also targets, so from the lab, which are bred. But then we come up with, actually we tested a few machine learning algorithms, and we come up, you can see that machine learning prediction was much closer to red than the lab that they have. And we reduced their mean absolute error from 0.73 to 0.43. They also said, that ROI, there is return of investment, was really huge for them. $18 million annually. And you can see, this is kind of how we present those things. Every single algorithm, vector auto-regression, random forest, artificial neural network. In this case, artificial neural network didn't have enough data, so it wasn't winner. But we show all of them, and when we told them, in this algorithm accuracy comparison, we think this would be your winner. So let's go quickly to surrogate data-driven deep learning models. So this is my research, so here we are combining the classical numerical methods with the this deep learning method. So we are using HPC to generate lots of this data in different scenarios, and then we train the model on GPUs, and then we actually bring those weights and biases trainable parameters to a laptop or any small machine, and then this happy guy, he can actually get numerical analysis results quickly, almost instantly on a laptop without modeling and simulation software. So I'm going to give you quickly some of the examples. So one of them is when you are making these composites. There is a frontal polymerization program process in manufacturing when you are creating these fiber reinforced polymer matrix composites. So this is a kind of fast forward where from chemical composition, we can actually get the front characteristics. But much more interesting, and this is actually going through, you know, solving these PDEs, partial differential equations, or ODEs. But much more interesting problem is actually inverse, where you know, what is this raising chemistry and the fiber volume fraction for desired manufacturing strategy. And you know, from the from the forward problem, we actually generated lots of data. Then we reverse. We said this, what was output becomes input for deep learning, and from what was you know, input becomes output, and then we train the model. And we published the paper with this. But what is important is actually right now we are trying to you know, make interesting this kind of method for the manufacturer of these composite manufacturers. Couple of others. This is actually in topological optimization. So topological optimization, we are kind of optimizing the shape of some structure with minimum materials, but still to be flexible and have enough strength. So we use that many scenarios created on HPC, and then train the deep learning model, and we're able to get instantly results. The other one is in this steel continuous casting, which was my research when I was doing my PhD. So their materials are even harder because there is a solidification, there is a viscoplastic phenomena. So here we use actually sequence learning. So we learn not only the relationship between input and output, but we are also learning all of these time dependency, load dependency. And we were able actually to get pretty good results last year in one of these papers. When it comes to turbulence, so here's another example where, you know, so this is kind of different way to do it. This is actually where we are not creating, you know, those bunch of these, you know, data from modeling, but we are actually using deep learning directly to solve the governing equations. And, you know, there is a new thing here in TensorFlow 2, which is called automatic differentiation, which help us actually to differentiate some of these things. So we can actually go directly into PD. We can create the PD partial differential equations, and then we can create the residual. And, you know, as deep learning network is learning, this residual goes down. So at the end, it's trained enough actually, so we can apply it and you know, get results directly with this physics informed. And there was also equivalent problem in solid mechanics. Again, you know, no data generation is needed for this kind of physics informed neural networks. Easier discretization. You don't have to solve the big system of equations. So we believe this kind of, you know, what we like to say, confluence of modeling, simulation, and artificial intelligence is going to be a big thing in the future. I think we are end of the time. So I'm just going to give you a few, you know, thoughts here that everybody says, you know, AI is going to be so powerful, right? So they also fail miserably. So, and just give you examples. You know, they tried to make machines read better than humans. It didn't work that way. AI health care, you know, IBM Watson has a Watson doctor, right? They also, you know, it didn't achieve what they thought it would achieve. And I think, but it's improving, no doubts about that. And it's fair to say that AI machines right now can learn, but not yet think, not like us humans, right? And it remains to be seen if and how the major AI singularity point of true intelligence will be reached. So I'll give you a little, you know, cartoon here. So what happened here, you know, everybody's talking about robots, yeah, and AI machines, they will rise one day, right, against us humans. So, you know, they rise, but but they attack humans with the spears and arrows. And, you know, because they look at the data, they said, oh, you know, for centuries, humans were using spears and arrows, you know, let's do that. But then humans were able actually, so we were lucky this time, right? I think Anna also told me, it's a good thing actually to provide you guys with some resources for learning, machine learning, deep learning. So the first one on my top where I learn is actually for free is a Coursera, and you should look for Professor Andy Eng courses. And then there are some of these sites easily found, like Towards Data Science, Machine Learning Mastery, Deep Learning book, where actually you can find lots of good examples if you're interested in doing that. And of course, you don't have to have HPC, right? I think most of my development I did on this laptop with CPUs, but then when I actually start generating lots of data, then I engage my graduate students to work on HPC. So you can learn all of this actually even on a laptop. And then I listed some of my favorite books in artificial intelligence and deep learning. So I think this is all going to be available, right, Anna? So people can see all of that. I thought maybe it'll be interesting to mention also HPC situation in Bosnia and Herzegovina. I was involved since 2014 in some of these things. Tradition is huge. If you ask your parents, your grandparents, they'll talk about EnergoInvest Iris PC16, which was on the pair with IBM at the time, sometimes even better. Unfortunately, war came and all of that was disappeared, right? Bosnia and Herzegovina itself has a cheap and available electric energy, not cheap for people who live in Bosnia, of course, but for the rest of Europe, I think it's relatively cheap. I also talked to BH Telecom, and they claim that that our communication network connecting with the rest of Europe and region is pretty developed. So that's also important. HPC centers are somewhere where labor is cheap, where there is a plenty of energy, electric energy, and where there is a good connection with the user. So I think Bosnia has all of those things, right? Of course, we have smart people, but right now probably we don't have enough HPC expertise, admins, parallel programmers. But again, we can learn all of those things quickly. Of course, major probably drawback is actually lack of political consensus concerning the national HPC advanced IT policy. However, they are enthusiastic people, and I know about small systems deployed at the University of Sarajevo. Mainly Professor Milošević from Primat and Fetic, and then Professor Torlak also has some lab at MEXI, at Mechanical Science Engineering, Professor Nosović from Electrical Engineering. I would also mention Dr. Dejan Vitlasil from Swedish National Infrastructure for Computing, huge BH Patriot, who actually sent the whole batch of these HPC machines to Prirodno Mathematički Fakultet in Sarajevo. I think they are still in use. So it's not zero. I think there are some systems, but we have to see how we can actually work and maybe make some more of HPC infrastructure in Bosnia. So this is actually, everybody knows Edin Džeko, right? So when he scored, when he was in Manchester City, he says, this is za moje mahalce, and I say actually this talk was za moje BH genialce. Thank you.
Thank you so much for this incredibly engaging presentation. It was a pleasure to listen to. So the first question we got was actually about half an hour ago. It is, how much DOF do average computers have?
How much they have what?
DOF.
DOF stands for what?
I will check right now.
Oh, degrees of freedom, you mean?
Oh yeah, that's what.
So we are talking here about numerical analysis. In finite element method, we use this notion of degrees of freedom. We are breaking this something like this stuff like into mesh and nodes and elements. And each of these nodes, if you are in 3D space, right, they're going to have a component in the Y and X and Z. Sometimes they have rotations too, and those are degrees of freedom. So when you count them all for all the nodes, you come up with this kind of total number of degrees of freedom that this structure has. And similar notion is also in a CFD in fluid dynamics. And at the end of the day, if you do these classical numerical analysis, methods, you have to actually solve that system of all of these together, an implicit, for example, method, and it ranges from few thousand, millions, and I show you actually in blue waters, that was kind of extreme. We actually solved a system of 3 billion degrees of freedom problem there.
And the second question is, when do you think the quantum computers will replace today's supercomputers?
That's a very good question. Unfortunately, I'm not, my research interests are not there. And actually the whole NCSA, we decided not to be involved so far with that. We think that GPUs and AI and all of these things are more important right now. But there are other centers in United States, in Western Europe, in China, who are actually working intensively on quantum computing. The problem there is actually most of these calculations are integer based, and they are great for integer rich calculations, and there's anecdote that once the first quantum computer starts working seamlessly, they're going to be able to hack all of these passwords that we right now in a fraction of seconds, because they're really talking about combinatorics of the integers, right? But anyway, there are some signs that quantum computers are going to be also be able to do and crunch floating point numbers. So when that happens, then I think the whole business is going to be quickly moving towards quantum computing and running some of these things maybe 1,000 or even million times faster than on petascale machine. But yet to be seen. There are some engineering problems there too, right? When you talk about quantum computing, your system has to be close to 1 Kelvin, 0 Kelvin temperature. And from engineering point of view, it's really hard to actually keep up with such a low temperature there. And any disturbance there is actually also influencing results. And there's lots of uncertainty with those results right now. But nevertheless, that's where the research money is going big time right now.
And a personal question of mine. Considering the vast potential of supercomputers, how do you see it impacting cybersecurity?
Oh, I was just talking about that. So quantum computing, definitely it's going to make a huge impact because people will have to figure out, this cybersecurity stuff from scratch when that happens. And, I'm pretty sure my colleagues in the Department of Defense and Energy, some of them don't sleep, right? They look at those things all the time, and they're ready for those threats. But in a normal scheme, I think people have people trying to protect these HP systems and all the time, and it's a big issue, and especially nowadays as we have these cloud providers like AWS and Azure, and they are making these huge HPC systems virtual machines, and there were some breaching there actually that happened because it's on this kind of environment, it's even harder to protect those systems. And versus us in academia, where we kind of have limited number of users, and we can easily we can find. I mean, we have a whole department which is just doing security 24/7 all the time, and they are doing pretty good job. But nowadays, again, being 100% protected, it's nobody can claim that.
And we have another question. Can supercomputer one day find their application with cryptocurrency mining?
So again, this comes to quantum computing, when it comes to cryptocurrency, people, we found actually some users, you believe it or not, academic users who were actually running some of those programs on GPUs, which they are not supposed to do that. But good thing, all of our users, especially from academia, they have a limited allocation. So they were running, and then they run out of allocations, and they were asking for more. But from their pattern, people were able to find that they didn't do their science; they were running cryptocurrency. So whether or not running these HPC system of petascale and an exascale level, for cryptocurrency, I don't know, because they are, using lots of energy, and maybe instead of somebody to become rich, I think there are better ways to use them, to find a cure for cancer, to be protected from tornadoes, and all of those things that we are doing nowadays. So.
And what is your take on investments that NVIDIA and ARM are doing in this space?
NVIDIA and ARM, they joined the forces, right? NVIDIA actually bought ARM. ARM used to be our partner, but NVIDIA it was before, so kind of, we joined their partnership, under NCSA. Yeah, I think it's a good thing. I think, ARM has lots of these compilers as a legacy. And what happened is actually once NVIDIA put their hands on those compilers, they were able to come up with OpenMP compilers 5.0, which nowadays can actually run independently. The same code, same syntax can run on GPUs and on CPUs. So I think it's, at the end of the day, end users will benefit. Whether or not it's going to reflect on a price of these compilers and all of those things. I heard actually that once NVIDIA bought ARM, some of these PGI compilers, they actually become open source. So that's a good thing too. So yeah.
And in your opinion, at which industry or science sector a use of supercomputing is underrated but could make a huge difference?
Probably life science more than technical. For example, I mentioned genomics, bioinformatics, even social sciences too. They are just discovering power of HPC. I would say bioinformatics, genomics, they started embracing HPC big time. But their code are probably on the level of engineering and science code 10 years ago, but they are making huge strides actually to make them more parallel. And I show you example on GPUs. So I think, once they have better codes, they already have good hardware, right? I think we're going to see more of the impact in life science and bioinformatics. Another one is in drug discovery. So pharmaceutical companies, big pharma, they are actually investing on HPC big time nowadays for discovering new drugs, interactions, and all of those things. So I think we're going to see more of that. And then I mentioned social science, social behavior, and all of those things. So eventually, I think they will also embrace some of the HPC right now. But of course, the leadership right now is in science and engineering, in more like a technical areas.
Are there enough data scientists and machine learning engineers available for these cross science types of work?
Interdisciplinary, what we like to say. Yeah, yes and no. Lots of young people are finishing computer science major, coming up with master's degrees, PhDs, but problem with them is actually they don't have domain expertise from these classical engineering and science areas. So, but they can learn. The other way around is like me, who actually was trained in a classical mechanical engineering and numerical analysis, who actually started learning, these machine learning, deep learning, a little bit from, as I show you some of these resources on the internet, but also from my colleagues who are computer scientists, and who were trained to do machine and deep learning. So I think, we're going to see both ways. I think we're going to see computer scientists learning domain to actually better apply it, but also, domain experts who are actually started learning about machine learning. Is there enough of this kind of hybrid talent? No. I think people who have this kind of talents in both worlds. I think it's going to be very valuable in a short, even in a longer time, on the market. Yeah.
And we have another question from Seid, adding to the last question. At what point does current machine learning, data learning, and AI become automated as a technology itself? With another hierarchical AI type of technology, and pardon me, deep learning?
That's a very good question. There are different predictions right now. Somebody said that within 20 to 30 years, we're going to train AI to do the AI. So we're going to be having actually layers of AI. And right now, needless to say, there are professions which are in danger, right? And so with all of these self-driving cars and trucks, I think, we're going to see actually when the legislation allows them to drive on the streets, we're going to see actually less taxi drivers, less truck drivers. But even before them, for example, when you look at the doctors, when you look at the radiologists, the convolutional neural network that I was not talking about, in computer vision, they are at the point where they are actually able to recognize tumor or cancer or whatever lesion. They are looking better than humans. So I think, radiologists are not going to be, replaced, but I think there will be less need for them. So now going back to this actually AI, even data scientists, right? At some point you will say AI is going to be so smart that AI itself is going to actually apply AI algorithms and start training these, things without humans in a loop. So we'll see. We'll see. It's interesting time, no doubts about it.
I've always been curious when it comes to these interdisciplinary projects, especially the ones that are related to natural sciences. Is it hard to find investors for these types of products, considering the fact that, like, in my experience, I usually see finance sector being the one that utilizes AI and data science the most?
I think, Anna, right now, if you ask me, where do I have more industrial partners who are actually funding our research, it's actually more in the life science, in pharmaceutical industry, Mayo Clinic. I mean, you can go to NCSA webpage, you can see who our partners are. They are actually more investing in research and these AI things, machine learning, data analytics, than technical companies like, Caterpillar, Boeing, John Deere, so I think, we are at the point where these natural science companies and corporations, they actually figure out the power of HPC, power of AI. So they actually started embracing it maybe in the last few years. Especially, I think even during the COVID, they were actually able to, many people couldn't go to labs and just, they actually, some of these things can replace labs, right? So they actually started sending people home, and people at home, they were able to do some of these analysis, and they were, CEO, CTO of these companies, they figure out actually they can be pretty reliable. So I think in a sense, all of these lockdowns and COVID help actually to propagate HPC and AI even more in the life science sector.
And we have another question. Pharma statistical analysis tools. Wait, okay. I had the chat scroll down a bit. Based on pharma investment, do you envision SAS and R jobs to go away sometimes soon? And then there's a clarification, pharma statistical analysis tools, SAS, and its open source peer, R.
No, I don't see it happening overnight. I think, people are figuring out, back to my, I think 2-3 questions before, when I was talking about AI, doing data analytics, I think it's not going to happen overnight. I think there's a whole process for that. So if, one of our colleagues who is probably younger, who is working with SAS now and, the open source equivalent, I think in terms of, job security, I think 10 years or maybe more, I think it should be safe, so, yeah.
So you have a big thank you from the person that asked the last 3 questions. We could give it another minute or 2 in case anyone else wants to ask any questions. Okay, that seems to be all of the questions. Is there anything you would like to say to the audience as a final word?
Not much what I already said, I think, we are, I want to thank first, Beha Futures for actually showing something that we already know, that we are very smart people, and that, Bosnia has probably most resources in actually in their human potentials. It's just that, us who venture outside overseas, we showed how much we can do it. But I think for people in Bosnia, if they set up their mind, to these big goals, I think, everything is achievable. It's just that, you just have to go one step at a time, and you don't have to for this HPC business, you don't have to have HPC resources right away, but you can learn on a small scale, machine learning, even classical analysis, and then you can engage this supercomputing power at some point if you have access to that. But I think people are really valuing that you don't consider these things as black boxes, that you actually know what is happening there, which algorithm is used, and coming to actually HPC and supercomputing is just it will happen. It will happen. I think our neighbors from east and west in Croatia and Serbia, they already have these centers. So I think it will come to us eventually too. And if you are ready and if you know what's happening, we're going to be in a good shape. I like to be optimistic.
Thank you so much. And it is truly of an incredible value to just have people like you come and share their experiences and demystify certain industries and what's actually happening currently without the filler information that the media usually throws in. Thank you once again for taking out your precious time to share this much knowledge. This was truly really, it was a detailed presentation, and it wasn't like I'm used to hearing lectures on these topics be more of an abstract, what could happen, but it was more concrete. I really appreciate this, and I'm sure many of our viewers do. So with this, I would like to conclude the webinar and wish you a great night, good night, or good afternoon over there.
Thank you, Anna, and thanks everybody for tuning in. And if you have any follow-up question, I think it's easy to find me on the internet too. So yeah, I'm connected some of you through LinkedIn too. So yeah.